guys, this video is about finding the nth Fibonacci number in a Fibonacci series. Fibonacci number series are represented by these numbers: 0, 1, 1, 2, 3, 5, 8, 13, 21, okay, etc. Now, these numbers follow a particular pattern, and that is, if you were to take any Fibonacci number, like for example, you have number 13. This 13 is actually the sum of 5 plus 8. If you were to take another one, for example, 3, this 3 is the sum of 1 plus 2, right? So we can kind of see, if you take any numbers, let's say the nth Fibonacci number, and that nth Fibonacci number is actually the sum of the n minus 1th plus n minus 2, right? These Fibonacci numbers. So that's really a series here. What we're trying to do here in this code is just to write a solution method that fetches the nth number in the Fibonacci series. So given that, there is also a couple of things that we gotta note, and that is F0 is 0. F1 equals 1, right? So as you can imagine, if let's say if we wanted to fetch the nth Fibonacci numbers, this requires a lot of recursions, right? Because what happens is you're gonna have to, basically, in order to find the nth, you have to find the n minus 1. In order to find the n minus 1, you're gonna find the n minus 2, n minus 3. In order to find n minus 2, you gotta find n minus 3, n minus, right, so on and so forth. So this is pretty recursive. And the base conditions that we have here is, right, because Fibonacci numbers, they do not have negative. These are the base cases that we have to consider. So with that, we can quickly write a recursion to illustrate this. So let me move forward with the code here. So this is our simple public class, and this public class has a console application that calls the Fibonacci number. So this solution method is encapsulated here. So let's just write out this entire Fibonacci method in this opshop. So the very first thing we want to do is to account for the base conditions, right? So we know the base conditions are F0 and F1 respectively, right? So if we do this, let's say if n equals 0, right? So we know for sure this returns 0, but what happens if n equals 1? N equals 1 return 1 at this point. So these are the base conditions, but other than that, we can simply just write out the whole formula here. This is the nth Fibonacci number, right? This nth Fibonacci number is actually the n minus 1, right, plus n minus 2 Fibo altogether, right? So this should give us the results that we need. So let's quickly run this, right, and see what happens. Okay, so as we can see here, the 9th Fibonacci number is 34. So if you do a count here and goes all the way up there, you'll see it. The 19th Fibonacci number is, right, this number. So let's just do a small test and see if, let's say, do 0, 1, and make sure at least the first couple of Fibonacci numbers they matches what we have here in red, right? And the second and the third, let's also do the 5th, right? The 4th. Okay, so this gives us 0, 1, 1, 2, 3, and that is exactly what we have here. So now that we've looked at recursion, let's turn the solutions into iterative solutions. We can readily do that, but since these base conditions could be much simplified, noting that if n equals 0, it returns 0, right? So this 0 is the same as n, and so is n. This n equals 1 is the same as this. So the above, right, could be written as if n less than equal to 1, right? You can just return n, right? Or you can say n less than 2. It doesn't really matter. So we can get rid of this, first of all. In order to turn this into a iterative solution, we have to define a couple of variables. And before we do that, let's look at our problem-solving step here. So if you were to take this, right, for example, number 2, right, as your Fn, right, for all intents and purposes, forget about this being 2, but Fn, right, is the sum of n minus 2, right? Plus n minus 1. So if you just add these all up here, you get Fn. So that's what I want to do. I want to make sure that, I can find a way, for example, starting at Fn at this point to iterate forward, right? And the position that I want to be at is, starting with Fn equals 1, right? At this position here, because we know that the both F0 and F1 would have been defined already. So that's my starting position. So let's look at this, right? Just say we are setting this positions where we already know Fn, right? Fn minus 2 is 0, and Fn minus 1 is actually 1. And then what we want to do is make sure that Fn, right, is Fn minus 2 plus Fn minus 1, right, at this point. The reason why I can do that is because if n is either of the first, right, first or second, we will have returned already. So by this point, if the execution has gone through the above, right, at 22, it would have gone into 24 and 25. And that would set Fn, right, the initial condition for Fn being 1, right, because 1, right, Fn is 0 plus 1, right? That's our starting point here. So what I want to do is, first of all, we can probably get rid of this, right? Because at the end, I want to return Fn. Okay, so what I want to do is write an iterative loop, right? So this is n equals 1, n less than n, I plus plus. Okay, let's look at the reason why this is the case. Well, we're starting with I equals, basically I want I to be Fn at this point. So starting point is where the very first location of it is. So if you count the number of iterations that we have to go through, either you start with I equals 1 all the way through n minus 1, right? Or we can go for I equals 0, right? Overall, we just need to have one less the iteration loop to establish this, right? Because we have the conditions already set. Okay, so this is what we're going to do. In order for this loop to go forward, either you have this, right? Well, we can start with I equals 1 all the way through I less than n. And this is what we want to do. Fn equals, right? This is the same thing, right, that we wanted to define up there. Fn minus 2 plus minus 1. And remember, this is being done every iteration. So what we want to do here, after this is forward, this is done, then we want to move our Fn minus 1, right, to the Fn minus 1, Fn minus 2 position to Fn minus 1 positions. So that's what we want to do. Fn2 now is advanced, right? Before we get into the next level, well, we have the Fibonacci advancement is to advance F2 as well as F1, right? So F1 after the summations above would have been Fn. So this is what we want to do. F1 equals Fn, right? So let's look at what's going on here. So as soon as I get my Fn, right, Fibonacci numbers, I want to advance my Fn minus 1 into forward by 1, right? So it's Fn minus 1, right? It needs to be advanced by 1 as well. So this will give us the conditions to move forward with the next iteration that adds these two numbers up to Fn. So if we just go by this, and then at this point, I just want to double check that we have the right solutions. Let me just add another use cases and run this again. We should be getting 0, 1, 1, 2, 3, 5, 0, 1, 1, 2, 3, 5, which is exactly what we need. So this is how we use iteration to solve this this problem. Let's look at the time complexity of this iterative methods. First of all, we immediately notice that this is O of n, right? O of n minus 1, but it's the same as O of n. This is time. And in terms of space, we're looking at these variables here and nothing else. So this is O of 1 in space, which is pretty efficient, and time-wise, this is not that bad either. Now, this is iterative methods. What about recursive, right, methods that we did there? Now, recall recursion requires a lot of call stack memory, right? The amount of memory that goes in there requires that basically every function that gets placed or method gets placed, invoked, it has to be on the call stack. So from a call stack perspective, and because we're talking about a number of them, and the solution for that one was actually O of n from memory standpoint, right? Which is much higher than what you would need with the iterative methods. This is the iterative method, right? So that's call stack. But in terms of the time, right? Recall that what we've got, right, is O of n. This is that, right, equals to the amount of time it takes to ascertain, fn minus 2, right, plus O of fn minus 1. It turns out that if you just add them all up here, this mathematically equates to around O of 1.6, which is the golden ratio here. This is the golden ratio to the n, right? So golden ratio n. So this is what we call exponential, which is super expensive, right? When you get into n equals 1,000 or something like that, at some point, you're gonna run out of memory. Your computer is not gonna be able to handle this. So this is really what's bad about recursions. But if you look at iterative methods and then recursion method, recursive method is generally very clean, right? It's easier to understand how this works. Iterative methods are generally cheaper in that regard. So this is also what we call the bottom-up approach, right? Iteration starts with the bottom, right, all the way to the high. So this is the bottom-up approach. Okay, so let's look at this recursive problem we just solved here, right? So using Fibonacci 4 here, as you can see, if we were to break this down into a graph, any computations for F4, right, involves the previous two, which is 3 and 2, right? And now if you recurse this in deeply, you can see F3 is F2 plus F1, right? And then F2 itself is F1, 0. So on and so forth. And as you can see here, there's a lot of duplicates here, right? We see F1 being called several times. Now, this is the case if you're using recursions like this, right? So it dawns on us, right, that if you're going to use this method to solve this problem, what if we pre-compute or maybe having some sort of mechanisms in place to store these things? Let's say if F4 were to recurse into these, this tree, these branches, that we can find a way to somehow persist, right, the information that we already know that we may come across that we want to just to compute this once. Yes, there is. We can set up a, for example, if this is a problem space here, right? And then we said that there is an n number of, values that we can compute. We can probably come up with maybe an integer array, right? So integer array, for F1, right, there's an element storing the value that we computed earlier, right? So the second time around when F1 gets called again, right, like this, we can fetch that information from that array, right? So in general, you can create some sort of dictionary, some sort of hash table, what have you. But easiest thing is to come up with a integer array that we can store this value from. So let's look at how we can solve this problem by turning this recursive method into that. This is what we call memoizations. Memoization is very, very important concept in dynamic programming. Okay, this means persisting informations, right, as we go. So let's look at this method in details here. So let's go back to this problem here. Let me just get rid of this because we don't really care about that at this point. We can preserve this. This is still needed. The very first thing we want to do is to have some sort of global memoization, some sort of array that stores these things. So what we can do is can set up a dynamic programming integer array, right? Let's say this is the integer. Now, because we don't know how many values there are, and it's dynamic. Let's just say, for 100, right? This is the only thing because we don't know how much we need. In the future, if you're running this in Java, you can also use array list, which is dynamic. But let's just assume that there's no more than 100, right, elements in there. So what we need to do is define our table and start using it. Before we do that, let's just set up our regular fn and fn minus 2. you don't really have to initialize this because we're going to be doing that next. In order to compute, actually not compute, but to find out whether there is fn-1 or fn-2 in DP, we need to initialize our table. But fortunately in Java, if you don't initialize your table explicitly by default, all of the elements inside of this integer array it's got a value of 0. So first thing we can do is checking to see if DP, right? At this point, we want to find out our f-2, f-1. So let's just say fn-1. Let's say if this is empty or not, right? So if this is not, right, 0, right? So at this point, we know that for sure this fn-1 is inside this DP table. Then we can set this one equals basically this, right? Right. But what if fn-1 is not in this DP table, this memoization table? We can just fetch it, right, using our recursion, which is else. Oh, so this is autocomplete. fn-1 is coming from another one, which is n-1, right? Okay, so this takes care of our fn-1, right? So we need to do the same thing for fn-2. So without having to type in all of these things, let's just fix this altogether. So in this case, we're gonna have fn-2 checking to see if this is in the table. If not, then we set it from the DP table. If not, then we go fetch it, like this, like so, right? So at the end, what we want to do is to make sure that our DP, right, has the most up-to-date value for n, which is fn is equal to fn-1 plus fn-2, right? So that's it. And then we want to return our, right, DP table at end location. That's what we're going to compute. Okay, so that said, we've got also our test cases set up already. Let's just run this and see what happens. Okay, so there's a couple of things that we need to fix. One is when fn-1 is have been initialized. So what we can do is to fix this by setting it to, you can set it to 0, it doesn't really matter at this point. Okay, and now this is what we got.